Okay, so this next session is about azimuth, which we will express as an azimuth angle, as a quadrantal azimuth, or as a true bearing. Okay, we've already talked about this in our introductory sessions the first couple of weeks, but now we will learn in practice how to calculate an azimuth, and I will explain to you why you need an azimuth. Okay, I'm sure you've all already calculated an azimuth when you were on the dart. Maybe this is a long time ago, but well, it will quickly get back to you. Okay, so azimuth in practice, why do we use the azimuth? Because during the watch, what can you do? You can take a bearing of the celestial body with your compass. It can be either a compass bearing or a gyro bearing, depending on what kind of repeaters you have on the bridge wings. Is it a repeater of the magnetic compass or of the gyro compass? Voila. And then if you have these bearings, the compass bearing or the gyro bearing, and you have the time of your observation, then you can find the equatorial coordinates of the celestial body that you've been observing. Okay, the equatorial coordinates, we all know by now that this is the declination and GHA and LHA. Okay, and what can we do then? With formulas that I will be demonstrating to you during this recording, formulas for azimuth, or with the calculated ABC tables in the Norris, what can you find? You can find a true bearing. Okay, this is your true bearing, and you know that. And if you have the true bearing and a compass bearing, you can calculate the deviation, or when you have a true bearing and a gyro bearing, that you can calculate the gyro error. Okay, voila. So this is what it all comes down to. You have either a compass bearing or a gyro bearing. Okay, then you get a true bearing. Where do you get it? Via the ABC tables or a formula. And then you can do the error between the compass bearing or the gyro bearing on the one side and the true bearing that you have calculated on the other side. Okay, the difference between the two of them is your error. Okay, the error, the total error, is either east or west. Okay, you know that you can find your variation on the chart. Okay, and then if you add or you determine the relation between error and variation, you can easily find either the deviation or your gyro error. Okay, so let's take an example here. For example, when you have a compass bearing of 109 degrees, that is here once again, and a true bearing of 115 degrees. The difference between the two of them is 6 degrees. You know that true bearing is compass bearing plus or minus the error. When the error is east, your compass bearing will be least. When the error is west, your compass bearing will be west. Okay, here the compass bearing is east, so my error is east. Okay, so I have a 6 degrees east error. Okay, when I've seen on my chart that the variation is 8 degrees east, you easily find, just by adding and subtracting, that when you make a drawing here, this brings you back to the first year. This is your true north, then your variation is 8 degrees east, so this is your magnetic north, and then they say that your total error is, this is your compass north, this is the error, and the error, sorry, maybe it's better if I should be, maybe do it a little bit more up to scale. This is your true north, magnetic north, because your variation is 8 degrees east, and your total error is 6 degrees east, something here. This gives you the compass north. This is your error. So you know that when you go from variation to compass, that this will be the deviation, and that the deviation is 2 degrees west. Okay, this is kicking on open doors. We know this already from 2 years ago. Okay, voila. So that's really why we need the azimuth in practice. Okay, then if we know the azimuth, we know voila, in which way we should look, in which direction actually we should look to find a certain celestial body. Okay, this will also help us in the future when we are doing intercepts. If you know the true bearing, you can determine lines of position. Lines of position are always perpendicular to the true bearing. I will explain this to you later on. And what you can also do, if you know what the true, if you see a celestial body and you know what the true bearing is, it can help you using the nautical publications to determine what kind of celestial body it was, which kind of star it was. Voila. Now, but the azimuth angle and the true, we know the relationship between the azimuth angle and the true bearing. The azimuth angle is an angle measured between 0 and 180 degrees. It's measured over the east or over the west, and it starts from the north when we are in the northern hemisphere, and it starts from the south when we are in the southern hemisphere. Okay, I feel like I'm reading myself, but it's very important that you understand this. Okay, then when we talk about the true bearing is the direction of an object in relation to the true north. Okay, it's measured, both azimuth angle and true bearing are measured on the horizontal plane. And the true bearing always starts from the north. Okay, measured in a clockwise direction from 0 to 360 degrees. Okay, well, and that you can measure by a compass. I should not forget to add, if you add corrections, and these are either the error or the gyro error. Okay, voila. So in the northern hemisphere, the true bearing is always measured from the north. Okay, so this is the true bearing here, and this is the true bearing there. Okay, the azimuth angle is always measured from the north in the northern hemisphere. That is here, and then it goes either over the east, as it does in this case, or it goes over the west, as it does in that case. Okay. True bearing always from the north, azimuth angle from the north in the northern hemisphere, and from the south in the southern hemisphere. Okay. True bearing always measured, the red arrow, always measured from the north. True bearing, let's say TB. Azimuth angle, when we are in the southern hemisphere, it's measured from the south over the west or over the east. Okay, but this we already know. Okay, and then how can we transform our azimuth angle into a true bearing? We've seen the same thing. We've already talked about this in previous recordings. When our latitude is north, our azimuth angle will be measured from the north, and then you are here in this case. The azimuth angle will be measured from the north, and so when it's over the east, this means that the east is in the front, so that your local hour angle is bigger than 180 degrees. When it's measured over the west, it means that your local hour angle is smaller than 180 degrees. Okay, and so in this case, in this first case, true bearing equals azimuth. In this case, true bearing 360 degrees minus true bearing is azimuth angle. Okay, so this is what is mentioned here. So we differentiate between LHA bigger and LHA smaller than 180 degrees. And then the second case, when we are in the southern hemisphere, true bearing is always measured from the north, but when our LHA, here it's measured over the west, so west is in the front, So this means that our LHA is smaller than 180 degrees. Okay, and so in this case, what do we have to do? We have to take 180 degrees to get the true and add the azimuth to get the true bearing. That's what's mentioned here. And on the other side, when the azimuth angle is measured over the east, this means the east is in the front and that our LHA is bigger than 180 degrees. So then our true bearing, we can also do it like this. What is it? It equals 180 degrees minus the azimuth. And that is what can be found here. Okay. Voila. And this is represented in another way. When the east is in the front, or when the west is in the front. When the east is in the front, we have a polar angle that is east. When the west is in the front, we have a polar angle that is west. And so we're in the northern hemisphere, so the azimuth angle is measured from the north over the east when the polar angle is east, and over the west when the polar angle is west. Okay. Voilà, so this is a small recap. Again, this is very important that you understand this. Now, let's go to practice. Azimuth angle can be calculated in different ways. You can either do it with the ABC tables, which is the most commonly used, actually, the most popular, although some students are afraid of the ABC tables. And then we have two ways of calculating the azimuth by a formula. Okay, the first one I will explain to you immediately, but it's the one that's used less often. Okay, so the first formula method, version 1, formula version 1, it can be derived from the navigation triangle. Okay. The azimuth that you obtain, it is mentioned here, via this formula is always the azimuth angle. Okay, that's the angle which is measured from the north in the northern hemisphere and from the south in the southern hemisphere, and that is between 0 and 180 degrees. Okay, how do we get to the formula? What do? You take a look at this general drawing where we have our navigational triangle, which is this one here. So the thing that we want to calculate actually is this small angle, which corresponds to this part here, which corresponds to this angle here. Okay, since we are here in this case in the northern hemisphere, and since our local hour angle for this particular example, our local hour angle is bigger than 180 degrees, so our polar angle will be east. The east is in the front, that is okay. So we have an azimuth angle which it starts from the north over the east. Okay, so what do we know from our observation? We know the position of our observation, that is our latitude. Okay, we also know the date and time, and this will allow us, what we have just done, to calculate for the celestial body the declination and the GHA, transform it into LHA and then to polar angle. Okay, voilà. So if we then take a look at what this information tells us about the navigational triangle, we see that when we know our latitude, I will use the same colors. I'll erase all the rest, it's maybe clearer. Okay. When we know our latitude, this is our latitude. From here to here, this is our latitude. Then we can also calculate our co-latitude. Okay, co-latitude is 90 degrees minus the latitude. Okay. When we know our declination, declination is the elevation above the celestial horizon. For that, I used the green. This is the celestial equator. This is the celestial equator. Elevation above the celestial equator is the declination, and the complement of our declination, 90 degrees minus the declination, is the polar distance, which equals this triangle. Okay, so we know col, we know the polar distance, and what else do we know? we know the polar angle. Okay, the polar angle is this one here, P. Okay, so and when we know 3 sides and 1 angle of a navigational triangle, what can we do? I've quickly read Mr. Buchan's course, and so you see that then you can use the cotangent rule in this triangle here. It is equal to that triangle that you see there. And so if you use this formula, you can obtain this here. So we know that the cotangent of the polar distance multiplied by the sinus of the colatitude equals the cosine of the colatitude multiplied by the cos of P plus the sinus of P multiplied by the cotangent of the azimuth. Okay, and this is actually what you are looking for. Okay, azimuth angle. Okay, it's this angle here that we are looking for. Okay, voila. So how do we do this? We started off from this formula here. Okay, it equals that one there. Okay, and then we bring this to the front. Okay, so the cosine of the multiplied by the cosine of polar angle equals the cotangent of the polar distance multiplied by the sinus of the colatitude minus, because we bring this to the other side, okay, the sinus of P multiplied by the cotangent of the azimuth. Okay. Then what do? We divide by the cosinus. No. We excuse me. We transform col into latitude, and we transform polar distance into declination, and this one here stays the same. So we know that the cosinus of col equals the sinus of the latitude, and we know that the cotangent of the polar distance equals the tangent of the declination, because 90 degrees minus col is latitude, 90 degrees minus polar distance is declination. Okay, so this, then we end up with this formula here, and then if we divide everything by the sinus of P, we have the cotangent of P multiplied by the sinus of L, so this becomes the cotangent of P. This stays the same. We multiply this by this, we divide this by this element here by the sinus of P, and then sinus of P, this is removed, so this leaves us with the cotangent of Z. Okay. I'll erase this once again. Then what do? We say that the sinus of L, we bring this to here. This gives us tangent of P, so this can be removed. We take the opposite, I mean not the inverse. Okay, so this gives us this formula here, and then we bring the minus cotangent to the front, and this to the other side here. So minus cotangent of the azimuth is sinus L divided by the tangent of P minus the tangent of the declination multiplied by the cosine of L divided by the sinus of P. Then we divide this whole lot by the cosine of L. This is an L. Latitude, maybe this is not clear enough. This gives us then here tangent of L divided by the tangent of P minus the tangent of the declination divided by the sinus of P. And then we see here in this formula that this element here can be considered as A, this element there can be considered as B, and the cosine of the latitude, we bring it again to the other side. Okay, and so we end up with this formula here. Okay, and so in this formula we say that this part equals A, that this part equals B, and then if we calculate this formula, we obtain an azimuth here, which is an azimuth angle between 0 and 180 degrees. Okay, and then if we say A minus B in this case equals C, we can write this formula a little bit more simple. We replace this by C, so minus the cotangent of the azimuth is C multiplied by the cosine of L. We take the inverse, so this gives us the tangent minus the tangent of the azimuth is 1 divided by C multiplied by the cosine of L. That is what we get here. And we put the minus sign to the other side. And voila, this way we can calculate the azimuth angle. Okay, there's only just one thing that you need to, which may be a little bit complicated or something to remember. Here, the signs of your latitude and your declination will influence the minus sign here. Okay, and it depends on the signs of the declination and the latitude, whether you have and the size of P as well, the polar angle. Whether it is smaller or bigger than 90 degrees. These are the three elements that determine whether you have to subtract or add A to B, or add A to B to A, or subtract B from A. Okay, but there are rules for this. Okay, two different cases. Either you have a latitude and declination which have the same name, okay, or you have a latitude and a declination which have different names. Okay, voila. So what should we do in this formula? This is part A, this is part B. We should actually determine the signs of all the elements in this formula as you have done here. Okay, so let's say we have a polar angle which is smaller than 90 degrees, and we have a latitude and a declination that have the same name. Then we can say, okay, tangent and of the L and tangent of declination, they have both a positive sign. Okay, when our polar angle is smaller than 90 degrees, we know that the tangent of P is always positive, and the sinus of P will also be positive. Okay, and then this plus stands for the cosinus of the latitude. The cosine latitude is always smaller than 90 degrees. Smaller than 90 degrees, so the cosine of an angle which is smaller than 90 degrees is always positive. Okay, so for example, I'm not gonna run through all these different cases, but when your polar angle is smaller than 90 degrees and latitude and declination have the same name, you have here a positive sign, and then here also a positive sign. So this makes, or this, the result of this is that your A value and your B value, that they need to be subtracted. Okay, and if you do this for all the other cases, for example, here when the polar angle is 90 degrees, we know that the tangent of 90 degrees is an infinite number, and that the sinus of 90 degrees is 1. So this gives us that this we don't have to care about, and then we know that we have here minus B as a positive value, but we have to subtract it, so this makes that we end up with minus B. Okay, if the polar angle is bigger than 90 degrees, these two remain positive, but if P is bigger than 90 degrees, the tangent will be a negative value. Okay, the sinus of an angle bigger than 90 degrees always remains positive, so this gives us a negative value for A minus B. Okay, voilà. And so then if you take a closer look at this, when your polar angle is smaller than 90 degrees, in this case here, you know that you have to do A minus B. If A is bigger than B, then C will be positive. If A equals B, there is no C. Okay, and if A is smaller than B, then C will be negative. Okay, voila. So C, maybe it's better if here I add 0. And then if you do the same thing for polar angle 90 degrees and polar angle bigger than 90 degrees, if you add this all into the formulas, you will see that when A is bigger than B, that your azimuth will be bigger than 90, azimuth angle, excuse me, will be bigger than 90 degrees. When C is 0, the azimuth will be 90 degrees. And when C is a negative value, azimuth will be smaller than 90 degrees. And you can do the same thing for all the different cases there. Okay? And then if we do the same thing again for the second, so this is latitude and declination, same name. Here you see latitude and declination, different names. So then we have to give the declination here a negative sign. Okay. Then again, we have the same cases, polar angle smaller, equal, or bigger than 90 degrees. And then we end up with this here, A plus B, or minus A plus B. Okay. So, and this will tell you, this is what will tell you, and this here, this and that will tell you whether in this formula here, if you have to subtract or add A from or to, no, B from or to A, okay? Voilà, but this formula that will be used then, and this, the result of that formula will always be an azimuth angle between 0 and 180 degrees. We'll do a practical exercise later on, okay? Then you can also calculate the azimuth with the ABC tables. No. Yeah. The version 2 comes later on. Okay. You can also calculate the azimuth with the ABC tables. Okay. They can be found in your Norris. Okay. Where you can find, first of all, A as a function of the local hour angle and your latitude. The sign, and a sign needs to be assigned to A, and they say that it is always named opposite your latitude, except when the hour angle is between 90 and 270. Okay. The second element that you need to find is B. B is in function of the LHA and the declination, and it always gets the same name as the declination, same name as declination. Okay. And then voila, you get a value for A, you get a value for B, and then by adding or subtracting these two arguments, you get C. Okay. And then C gets the number of whichever is the greater. So if you have a value of A, which is 2.7 north, and B 1.3 south, for example, then you have to subtract, and this will give you then 1.4. It gets the sign, C will get the sign of whichever is the greater, so in this case it's north. Okay. And then with this value, you try to find this value 1.4 in the table C, and then there you will find the quadrantal azimuth. And this quadrantal azimuth will take the sign of the C and of what? Of your polar angle. Okay. And so quadrantal means that the values that you obtain here will be between 0 and 90 degrees. Okay. So here, the first table is table A. I suggest again that you open your your Norris and that you see here. Here you can find the latitude. This here is your latitude. And this here is the hour angle. All these angles here are hour angles. So, and then if you make a combination of an hour angle and a latitude, you will find there the value for E, which is, as it is mentioned here, named opposite to latitude, except when our angle is between 90 and 270. Okay, and so please pay attention. All you need to know is actually included in this table. Even the signs that you have to give to the numbers that you simply just have to read and copy on your paper. Okay, voilà. So that's table A. Then, if we go to table B to find B, we will see that table B is also in function of the hour angle, but the second element is the declination. Okay, B is then again a combination of hour angle and declination. You just read a value there, you extract a value from the table B, then you get the value for B, which is always named same as declination. Okay. And then you have A and B. Adding or subtracting will give you C. C will take the sign of the bigger of the two. And then we go to table C, where you find an example page on this slide now. Table C is in function of the C value. This is C, and of your latitude. So if you have a latitude of 40 degrees and a C value of 2.5, then this is the, I will erase this, then let's say 27.6 is your quadrantal azimuth, 27 degrees 6, and it gets the sign of C sign, and the second sign is the sign of the polar angle. Okay, so C is north or south, polar angle is east or west. Okay, and should you be in stress at the exam and you have your Norris with you, you see that all you have to do is, regarding the signs is mentioned here, so the azimuth takes the combined names of C correction and hour angle, and if A and B have the same names, you have to add. If A and B have different names, you have to subtract. Okay, and C gets the greater of these quantities. So I suggest again that you take your Norris with you, and that you try to look this up yourself. Okay, so we first had a way of calculating an azimuth with the complicated formula. Then we have the ABC tables, and then we can make a combination of both. Okay, we know that this is our formula. Okay, so what do? First, we can calculate with our calculator A without having to worry about the ABC tables. I don't know, this is not very difficult, but never mind. Some of the students are scared of opening their books. Then you can calculate B, but then you have to give a sign to A or B. Okay, again, A is named opposite to latitude, except when our angle is between 90 and 270. B is always named same as declination. This is to do with opposite to latitude, depending on the hour angle. Okay, and then voila, you can decide on the signs of A and B, and these will tell you whether you have to add or subtract there in order to obtain C. Okay, you simply just follow then the same rules as for the ABC tables. Okay, and then you can just say, okay, my cotangent of the azimuth is C multiplied by the cosine of L. And if you calculate this, what you obtain is the quadrantal value of the azimuth, okay, where the first sign comes from C and the second sign comes from your polar angle. Okay, so 3 ways to calculate an azimuth. I know the most popular one is the ABC tables. The runner-up is the version 2 of the formula, and I hardly ever see anyone using the first formula. Okay, voilà. So now I'll try to demonstrate what we have learned so far by doing an exercise. First exercise is on the 20th of October 2020, where we do an observation. We take an azimuth of the sun. With our gyro compass, we take a bearing, and the bearing says 126 degrees. Okay, you're being asked to calculate the DG, the gyro error. Okay, you know your latitude and longitude, and you know the time of your observation. Watch time 8:05, chronometer time 11:37.50. Okay, so how do we start? We first transform our longitudes into time. Okay, so this gives us in total 33 hours and 30 minutes. Okay, that we have to apply to our watch time. Our longitude is west, so Greenwich is best. So what do? We add our longitudes transformed into time, and this gives us 11 o'clock 35 minutes 0 seconds. Okay, this we use. This is our, no, that we don't use. We use our chronometer time, And we know, since this is AM, that our chronometer time is also AM. Okay, so we go to the daily page. Did I include it? Not? No, so you have to do this yourself. We go to the daily page of the 20th of October. So I suggest again that you will take your nautical almanac and that you follow along with me. So on the 20th of October at 11 o'clock, we see that our GHA is indeed 348 degrees, 49.3. Our decorrection is 0.9, and our declination is 10 degrees, 35.2 south. Okay. The next hourly value is bigger, so we know that our declination is increasing. Okay. Then, this is the value for 11 o'clock, but we're not doing our observation at 11 o'clock, we're doing at 35 minutes later, 11:35. So we have to add increments. So we go to the back of our nautical almanac to find the increments. 35 minutes, 0 for the sun. This gives us 37, excuse me. It's 37 minutes. 37 minutes for the sun. This gives us 37 minutes 15. No, 37 minutes 15. So this gives us 9 degrees 18.8. Okay, this is the value that you are looking for. 37, 15, and this corresponds with this value here, 9 degrees 18.8. Okay, we always add the increments, and this gives us a GHA that you can see there. Okay, our longitude is west, Greenwich is best, so we need to subtract our longitude in order to obtain the LHA. This gives us an LHA of 305 degrees 38.1, bigger than 180 degrees, so our polar angle is east, and it's equal to 360 degrees minus the LHA. Okay. Voilà. For our declination, we also have to go back to the 37:15 seconds increments table. 0.9 becomes 0.6. We add that to 35.2, and this gives us then a southerly declination of 10 degrees 35.8. Okay, so this is, as I told you, the start of everything. Now we can start calculating. Okay, first we take the ABC tables, where in function of our polar angle and our latitude here, we find a value of 0.79 south. Okay, that we include here. Okay, then we go to the second table, where with our hour angle, our polar angle is 45. I forgot to change this. It's 45.21.9. Excuse me. Okay, and our declination, then we find a value of 0.22. Okay, the first A is named opposite to latitude. Our latitude is north, so A will be named south, and our declination is north, so B will also be named north. Okay, so this is how we get our declination is south. Excuse me, I forgot to change these things here. Our declination is south, so our C value, our B value will also be named south. Okay, so it's mentioned correct here, but on the pages of the novice, I forgot to change the signs with the values of last year. Okay, so then if A is south and B is south, we have to add A to B or B to A in order to obtain C, and C takes the sign of the greater, so in this case it's south. Okay, then if with this value we go to the C table, we find an azimuth of 55 degrees 0.8. South comes from our C and east comes from our polar angle. And so if we have south, east, 55 degrees 0.8, we will have a true bearing always measured from the north, which is 124 degrees 0.2. Okay, so we go to the C table. 1.1 is somewhere in between. Our latitude is 47.30, so this gives us approximately 55.8 for the azimuth. Okay, south from C and east from E. Okay, so please pay attention. I will change these values here in the PowerPoint, and then I will put a corrected version on Blackboard. Okay, so this is our first result. First method of calculating the azimuth with the ABC tables, we obtain a true bearing of 124 degrees 0.2. Okay, and so our true bearing is 180 degrees minus the quadrantal. This is the quadrantal azimuth. This means that it is between 0 and 90 degrees. Okay, the azimuth angle is between 0 and 180 degrees. Okay. So then the second method to calculate this is with a formula. This is the formula, the main starting point. So what do? We calculate the tangent L divided by the tangent of P. This gives us, this equals that. We calculate the tangent of the declination divided by the sinus of P. This gives us that. Okay. We know that in this case our latitude is north, and our declination was south, if I'm not mistaken. So, as is mentioned here, latitude and declination have different names, and the polar angle is smaller than 90 degrees. So, if I go back to my overview, a couple of slides ago, I know that my latitude and declination have a different name, and that my polar angle is smaller than 90 degrees. So, what do I have to do? I have to add A to B. Okay, so that's what I will do. Where is it? Close your eyes, please, or you will get drunk. So I have to add A to B, this mentioned here. And then we know that A is bigger than B, so my azimuth will be bigger, azimuth angle will be bigger than 90 degrees. Okay, so then I multiply this whole lot by the cosine of my latitude, and this will give us then this value here, and then the minus sign is it gets put it on the other side. Okay, and I take the inverse of the cotangent of that value there, and this gives me a negative angle. Okay, this is my azimuth angle. You have learned from Mr. Buchan that when you're solving a navigation of a spherical triangle, when you get negative values, that you have to add 180 degrees. And so this will give you an azimuth angle of 124 degrees. 0484. Okay, we know that our latitude is north, so we are in the northern hemisphere, so our azimuth angle is measured from the north, and we know that our polar angle is east, so the east is in the front and it's measured over the east. Okay, so this is my azimuth angle, and it equals my true. Allez. It wants to be something like this, so I just leave it. So it equals my true bearing of, 124 degrees, 04.47. Okay? Voila. So this is how I calculated this with this more or less complicated system here, with the first complicated formula. Okay? And then I can also make a combination of both. So first I calculate A, then I calculate B. Okay? I use the same method as in the ABC tables to determine the signs. So A is named opposite latitude. My latitude is north, and our angle is not between 90 and 270. So sorry, latitude is north, so A is south. B is always named same as declination. My declination is south, so B is south. Okay, and then if A and B have the same signs, you have to add. That's what we do. We add A to B, and then we get for C this value here. Okay, and then if you add that into this formula, again, you obtain a quadrantal value for your azimuth. Okay, and the quadrantal value will be south from C, E from east. Okay, and then again, if you have a quadrantal value here, south, east, and your true bearing will be here 124 degrees, 0447. Okay, in this case it's the same, but the only difference here is the angle that you obtain here will always be smaller than 90 degrees, and the angle that you obtain here is can be between 0 and 180 degrees, as you see, which is the case here. Okay, voila. And then to finish, I'll give you another example. It's more or less the same, but what have I done? The only thing that I have done is I have changed the sign of the latitude. So now, in the first exercise, if you allow me to go back, in the first exercise, latitude and declination have different names, okay, because my latitude is north and the declination here is south. But now, I've only changed the sign of my latitude. Now they have the same name, and as we will see later, the polar angle that we calculated is bigger than 90 degrees. Okay. Voila. So, what do we get? We get again ABC tables. We get the same values. As you will see, the only thing that changes, sorry, it should not be bigger, it should be smaller. Something that I have to change. For A and B, you get the same values. Okay. The only thing that changes is that now our latitude is south. So when we name it opposite to latitude, we will see that our A will not be south, but it will be north. B gets the same name as declination, or declination remains south. So again, we have a B value which is 0.22, but south. Okay. Now we see that they both have different names, so we have to subtract. This gives us a C value which is north, the biggest of the two, of 0.55. And then if we take a look at this in the C tables, we will find there an azimuth which is north, east, that's from the angle, and north is from the sea. And so this gives us a true bearing of 46.9. Okay. Second way to calculate this is with the complicated formula, where we see now that latitude has the same name as the nation. And then, if you allow me once again to go back more and more up, we now see that latitude and declination have a different name, that the polar angle is smaller than 90 degrees. So what do we have to do? We have to subtract B from A. Okay. Where is it? You have to subtract, as I told you, and we know that A is bigger than B, so again the azimuth angle will be bigger than 90 degrees. So first we calculate this. This is this value, then we calculate that, which gives us this value. We have to subtract that we know. And then we multiply it by the cosine of L. Okay, it gives us then this value. We bring this minus sign to the other side. That is removed. Then we take the inverse, and this gives us then again a negative value for the azimuth. We have to add 180 degrees to obtain this value here. Now we are in the southern hemisphere, so the azimuth angle is measured from the south, and here, because our polar angle is east, it's measured over the east. Okay, and this gives us then again the same value as we obtained here. If you have a southeasterly southeast in this case of 110 degrees, this gives us a true bearing of, what is it, 69 degrees and something. Okay, so we obtain the same value for the true bearing via the complicated formula, but you have to know how to apply these rules. Okay, then thirdly, we make a combination of A, B, C. We calculate first A, then we calculate here the value for B, and you will see, okay, these are the same values as what we have obtained here. Okay, we get the signs same way as we do in the ABC tables. Latitude is south, opposite to latitude, so A is north, B same as declination. So we have to subtract B from A. B is the bigger, so A is the bigger, so this gets a northerly sign. If we add this into this formula, then we again get an azimuth of north from C, east from the polar angle, which is 69 degrees 10.04. Okay. And then there's even a third example, but we'll finish here for this recording, and then next week we can recapitulate to this chapter and then do this third exercise, okay, as a matter of repeating. So good luck, and again, questions, don't hesitate to ask them in the live sessions, okay, or ask a question in the discussion forum. Good luck.